Hello YouTube. I'm going to try and do a repeat of video I posted last night because last night I was speaking a little bit too quietly for the microphone to pick up in an effort not to wake my wife up. So and people have complained that they can't hear it very well. So the video that I'm looking at is one called Flat Earth, 65 miles, Isle of Man from Blackpool at sea level. And it was put up by P900 Coolpix, 29th of June. Now I know others have commented on this and looked at it. I thought I'd add just a little bit to the conversation, maybe a little bit of extra information, and particularly wanted to use it in demonstration of a new Earth curvature calculator and demonstrator, which I think is excellent, well worth people paying attention to. So the video in question placed a P900 on the sand at Blackpool, presumably at some time when the tide was at least partially out, possibly all the way out. Low tide. I'm not sure how far out on the sands they went, and the camera's placed very close to the sand, if not directly on the sand. I imagine they would be sensible and actually have it up on something an inch or so just to protect the camera itself. And you can see that the sea is pretty close by here. It's not very far above the level of the water, but is a little bit above the level of the water. But I don't have a big issue with camera height. It's about as close to sea level as you can get. And the pictures from the camera confirm that with these waves. Just mute the sound on that. There we go. These waves coming in. They're not big waves, but they're still in the view. Because they rise up and fall down, they obscure the horizon somewhat. But as the video plays on, the horizon comes into view as the waves come into the shore. The horizon comes into view, and we can see, just go back a tad here. I'll keep it playing. Okay, there we go. Well, we can see the horizon. We can see 1, 2, 3, 4 wind turbines, and we can see a piece of what appears to be a piece of land here, occupying some part of the center of the field of view. It's difficult to tell because it's hazy whether there's a little bit more land over here and a little bit more land over here. There may or may not be. It's a little bit hard to tell. I've looked at the video quite carefully. I haven't tried to do any enhancement on stills from it. I haven't had time for that. But as you see, as you click on through the video, there's definitely something there. And initially I questioned whether it was indeed the Isle of Man. Looking on Peak Finder, if we place so this is looking towards Snaefell from Blackpool. If we put the camera at 0 feet, we're now pointing back at the Lake District hills here. As you pan round towards North Wales, you don't see any sign of Snaefell at all on the Isle of Man, and you get all the way around to the Welsh mountains here. And I thought that the camera might have been pointed at the Welsh mountains from Blackpool. It's a similar distance to the Isle of Man, and these mountains are much higher, and so would be more likely to be visible, and as Peak Finder shows, they are visible from 0 feet. And there are wind turbines in this area, but the wind turbines in that area are a little bit further away from Blackpool than the ones between Blackpool and the Isle of Man, and so I don't think that the camera is pointed in this direction. I don't think the wind turbines that we're seeing are the ones in this area, because they'd simply be too far away to be visible over the curve. So going back to the video in question, well, we'll just have a little addition on Peak Finder here whilst we're at Peak Finder. So if we alter the camera height, and we'll put it up to 20 feet. And we see that Snaefell at a camera height at 20 feet, 20 meters, starts to appear, but it's only the label that's there. It's barely visible. Perhaps with a lot of zooming in, you just start to see the peak of Snaefell. Snaefell itself is 261 meters, or 2,037 feet, just over 2,000 feet on the Isle of Man. So, going back to our video, if this is indeed part of the Isle of Man and Snaefell, then what does that say about the shape of the Earth? Well, a video maker has posted some confirmation that they were indeed at Blackpool. No real confirmation that they're looking at the Isle of Man, but I think they were. We can believe that, and there's no reason why they should be lying about that, so that's okay. And they pumped the numbers of 0 eye height, which is perhaps a little bit incorrect. I think a height of 1 foot would have been a little bit more accurate. And a target distance of 65 miles. And this gives a target hidden height of 2,817 feet. That's nearly 800 feet more than we should expect if we're seeing any of Snaefell at all. Now that would appear to be very bad news for the spheroid Earth. The calculator is predicting that we shouldn't see Snaefell, and we do see Snaefell. I think at this point it's useful to mention the shortcomings of curvature calculators. They all based the shape of the Earth on a sphere. Most of them use a radius of 6371. Some use a slightly different radius, but that's not too important. The point is they're using a sphere. We know that the Earth is a very slightly oblate spheroid, so it's not quite a perfect sphere. And we also know that it's not quite regular in shape either, that the surface rises and falls in all sorts of places around the Earth, such that it doesn't follow a perfectly smooth curve. Now, the extent of this rising and falling is small, and over the size of the whole Earth, it's pretty insignificant. But on a local level, it is could be fairly significant. A change in relative height between 2 points of a few meters can make a great deal of difference to the extent of where the horizon would be and how much would be seen beyond the horizon. So that has to be borne in mind. Curvature calculators are a great guide, but they are a guide. They are not designed or not expected to give 100% perfect values. Now, the next point to make is that water on the Earth, in the oceans, will not conform perfectly even to the gravitational shape of the Earth. So water is obviously affected by gravity, and that's what holds the oceans in place, and enables them to sort of stick to the ball, as the flat earthers like to call it. The gravity is greater or lesser in different parts of the Earth, and so that will affect the shape that the oceans actually have in those locations. Gravity, if you remember, is due to mass, and or proportional to the mass of an object, and the mass of the Earth is by far and away the greater mass in this case than the mass of the oceans. And so we have to sort of bear in mind that there's another reason why we shouldn't expect a perfectly spherical model to give us accurate answers. Would any answers be inaccurate to the tune of 800 feet? Well, I can't say for sure, but I don't think so. I think we'll be talking inaccuracies of that might rarely be several hundred feet, but probably not as much as 800. But that's pretty much my guess, my feeling about it, on the basis of the evidence and data that I've observed. It may be that larger discrepancies are possible. But on this occasion, I think it's reasonable to say that we're still looking to find several hundred feet of missing curvature, and we need an explanation for that. Now, this calculator doesn't take into account refraction, and everybody knows that refraction occurs. It's easy to demonstrate both in a laboratory setting or a controlled setting, and also in nature. Mankind has been observing mirages and looming and other refraction effects for, well, as long as mankind's been walking the earth. So does refraction, how much does refraction answer this particular question? Before we go on to that, let's just have a quick look, I forgot to do this, and confirm the location that we're actually looking at. So here is the North Sea again, with the Isle of Man and Blackpool. And what I've done is overlaid accurately the West Duddon Sands wind farm here. And we can see that our line of sight to the tallest point on the Isle of Man, Snae Fell, is just to the left of this wind turbine here. And we know that the picture has 4 turbines in it. One just in from the left-hand side, and then 3 turbines that would appear just to the right of the center line, with one going right to the edge, of right-hand edge. And if we look back at the video, we can see that we have a wind turbine right at the right edge. We have 2 other turbines that are on the right-hand half of the video, and one close to the left-hand edge of the video, with the high point of the land we're looking at just to the left of this turbine, the second turbine in from the left. So that would seem to agree very well, and we're looking across at the Isle of Man. The outer 2 red lines define our field of view, and we know that the land we can see is located from about this point to about this point. It occupies about half of the field of view, with Snaefell Peak being in the centre. Now, we can't tell where this line should be or how far down the hill we're actually seeing, but we're not seeing a huge height, it would appear we're seeing the top portion of Snaefell, something like this. So moving on to consider what refraction might tell us about this. And here's where I want to go to Walter Bislins' new he calls it Advanced Earth Curvature Calculator. Now, if you haven't found Walter's site yet, please check it out. I'll put links in the description for the calculator and for his blog. He has his blog in German and English, and there's lots of resources on the blog of various observations that have been modeled for flat and for curved Earth, and you can go there and you can see what you think of the observations and whether they better match a flat Earth or a curved Earth. But we now have this calculator, and we've set it for the globe, and we're going to set our observer height at 0.1 meters. So that's just a few inches, about 4 inches. In fact, I think I'll put it at 0.2 because that's a little bit more realistic. Still less than a foot above the ground. Our target distance in meters is 104,000. It's 104 kilometers from Blackpool to Snaefell on the Isle of Man. Our target size is 621 meters. That's the height of Snaefell, above normal sea level. Now, we know the tide was out, so actually Snaefell's height is likely to be a few meters higher than that, but we'll stick with 621. It won't be very many meters higher. And we'll leave the refraction set at 0. And we're at the moment zoomed all the way out, and the model shows I haven't actually added the target size, so we'll put that. There we go. So we've added the target size now and the distance. So zooming in on our horizon, we quite understandably don't see Snaefell, no matter how much we zoom in. And again, it would appear that the globe model has some problems here. But let's put the zoom in a bit just to help us out. What happens when we add some refraction? So by moving the refraction slider, and we add some refraction, now I'm starting to see the numbers appear. That doesn't mean the object has appeared yet. And as we get up to about 0.25 on the refraction, we start to see the object appearing. And as we continue, it protrudes more and more above the surface. Zooming in, we can see plenty of the object showing above the horizon, and with a bit more refraction, more and more of it will show. So we know that with some refraction, we can get the object to appear above the horizon. And the amount of refraction is greater than average, but is not absurdly excessive. It's simply an amount that, well, it gives here the refraction angle, which I think changes as I change. Yes, that's right, it does. The refraction angle is 0.15 of a degree is the amount of refraction that's going on, which is not excessive at all. Not so great that you would distrust it and say that couldn't happen just due to atmospheric conditions. Now, the beauty of Walter's model is that, or calculator, is that he has a flat Earth calculator as well. And on a flat plane, keeping all the parameters exactly the same as we had them for the globe Earth, we see the whole of the block from top to bottom. Full 620 meters is visible. The same amount of zoom, obviously we can zoom in closer and zoom back out, but the whole block is visible regardless of the amount of zoom there. 621 meters visible above the horizon. And placing the two side by side and trying to imagine that the blocks that we're looking at are the island of the Isle of Man, we can see that a far greater amount of the Isle of Man should be visible. The whole of it should be visible on the flat Earth. And depending on the amount of refraction occurring, more or less of the block or the island should be visible. So we would expect that sometimes it would not be visible, and on other occasions, small part, very small part visible. On other occasions, you might expect if refraction was, refraction angle got up to 0.18 of a degree, for example, or 0.2 of a degree even, you'd expect a significant portion of the top of the Isle of Man to actually be visible. Notice it's the top of the block that's visible. This is not the whole block reduced in size. So which of these most closely resembles what we actually observed in the video? Well, to me, we can categorically, I think, state that this is not the whole of the Isle of Man. The whole of the Isle of Man should be a little bit taller than this and would extend right off view to left and right. And if we panned the camera left and right, we should be able to see the full extent of the Isle of Man if the Earth was flat. Now, I've done a little bit more modeling of this myself. I've tried to do a scale model in PowerPoint. I found the only way to get it onto a single page was to have the scale so dramatic that it would be impossible to see anything at all, even zoomed in. And I can't put this on full screen because I'll only get the bit that's on the white square. But I've tried to draw to scale, and this is the flat Earth version. See, we have a little block here, which is the wind turbine, and in the background, the island that's the Isle of Man, away off here to the side. And hopefully this is at, I've not made any errors, and this is accurately to scale, or as accurately as I can get it. I've drawn a couple of lines on here. The red one is the line of sight to the top, and the yellow one is the line of sight to the base of the triangle that represents the Isle of Man. One aspect of this that might not be to scale is the width of the Isle of Man here, because I didn't think it mattered, but the height is to scale. If we zoom in, keep doing that, here we go. If we zoom in, just move down the page to get to where we want to be, you can see that we have a little block here which represents the height of the wind turbine. At the left edge we have the origin of the two lines. The top line goes directly at the top of the wind turbine. The bottom line runs right along the flat surface of the water as I have drawn it. And if we go right up to the far end, we see that the red line ends somewhere near the top of the island, and the yellow line hits the bottom of the island. So in our video, we should expect to see the top of the island at least at the level of the turbine hub if the Earth was flat. We should also expect to see this island, this land spreading out far more from side to side, because the whole of it should be in view. The curved Earth version, I need to zoom back out again. The spheroid Earth version looks like this. So we've used exactly the same size of island. We've used exactly the same block for the wind turbine. And although the blue here might look to be flat, it is in fact curved. The dimensions of the circle that's used here are proportionally the same as that of the Earth. And the first thing to notice is that the red line of sight here, which we can see without zooming in, goes to a point, so this is a straight line of sight, goes to a point that is above the island. And again, if we zoom in, we discover that that red line hits the top of the wind turbine block, and it goes to above the island. And looking back at our view here, if you imagine your line of sight to the top of the island, going over the top of this wind turbine and extending off into the background. Hang on, I've hit that. The top of the island, we're seeing the top of the island below that height. Our line of sight through here should go to sky and not to the island, and that's exactly what we do observe. So this further confirms that the spheroid Earth model more matches reality than the flat Earth model. Now, the pink lines that are drawn in here are curved lines, and they are designed to indicate how a bit of refraction could affect light coming from reflected from the island towards the camera. And the top line is a little bit below the top of the green triangle, the island, and the second pink line is somewhat further down. In this particular example, both lines managed to get all the way, they pass some point through the height of the turbines, and they get all the way to the point of origin here without hitting the water. Or they hit the surface of the water just at the point where the camera would be, or close to the point where the camera would be. So in this particular example with this particular shape of curve, anything reflected that is below this lower line would hit the water and not reach the camera. anything above the lower line would reach the camera and therefore be visible. Now, I'm not claiming that this is an absolutely perfect demonstration. The nature of these curves, the nature of the refraction of the light from the island is not known, and it would be foolhardy to suggest that this is a perfect representation of what's happening to get the light from part of the island to the camera. But it gives you a good feeling for what could be going on, or something similar to what is going on. So this modelling more matches what we observe in reality, a spheroid Earth and a flat Earth. Walter's calculator, what we observe more matches his globe calculator than his flat Earth calculator. And the last thing I want to do is, on Walter's calculator, is to consider the wind turbines themselves. Now, the wind turbines themselves are a different distance from the observer and a different height. Now, we know the height of these. I could try to confirm that, but I won't just now, just to save time on this video. But if anybody wants to check, they can do, and ask in the comments, and I'll explain how to check. The distance to the observer is 30 kilometers. That's taken to the middle of one of the turbines is a little closer, a couple of them a little bit further away, but basically we're looking at 30 or 31 kilometers to the turbines. What does the video tell us about the turbines themselves? Well, if you look at the height of the blades of the turbines, length of the blades of the turbines, you can see that they are longer than the height of the tower that we can see. Now, this doesn't mean that the blades are going down into the water. It means that a portion of the tower is hidden beyond the curve. And the towers are 90 meters to the hub here. The blades are 60 meters long. So we know that the height that we're actually observing is probably something like 40 meters, with about 50 meters hidden below the horizon. What does the curve calculator tell us about objects of those size? Well, we'll keep our observer height the same. We'll change our target distance to 31 kilometers. We'll change our target size to 90 meters, and we'll put our refraction, let's put it at about 0.3, something like that. So that's, well, let's put it at 0 to begin with, and then we can move it back up and see what difference the refraction makes. So if we do that, we see that we should indeed see part of the 90-meter tower. The question is, how much of that tower are we seeing? And the easiest way to demonstrate that is to change our observer height. And as the observer height rises, the tower rises. So what we're seeing at 0.2 meters above sea level is this much of the tower. Now, that's actually not very much of it. That's only possibly a quarter, possibly a bit less than that. But if we add the refraction, we start to see more and more of it. Now, if we put the refraction, say, about 0.3, we're now seeing, I think, roughly half of, or just a bit less than half of the tower. Yeah, half is where the yellow is, and we're seeing just a little bit less than half. So that helps to confirm what level of refraction was probably going on at the time, and confirms that we're seeing about 40 meters of the tower, with the remaining 50 meters hidden below the horizon. If we look at the flat Earth version of the same thing, the whole tower should be visible. And we clearly cannot see the whole of the tower. Putting the two side by side, and we ask ourselves, which is more in keeping with what we observe in reality? And the answer is definitely the globe Earth, or the spheroid Earth model. Is far, far more, well, this is a spherical model, but spherical model of a spheroid Earth. It's far, far more accurate than the flat Earth model. So that's all the evidence that I want to add to the discussion, to the debate, such as it is. Coolpix, or P900 Coolpix, you seem to have produced a video here which adds considerable evidence to support the globe shape of the Earth and not the flat shape of the Earth. So thanks very much for that. As I said, you've got another video out which does much the same thing, looking from Blackpool towards the hills and the Lake District and Cumbria, and it's a pleasure to watch your videos and to be able to demonstrate how they confirm that the Earth is indeed a sphere. So with that, I'll say goodbye, and hopefully this one can be heard, and I can maybe I'll maybe leave the other one up because it's done slightly differently, and anyone who can hear it can play both of them and see what they think.